Welcome to this particular module, and the lecture is on oscillators. So, what we have seen in oscillators? We have seen the criteria that a op amp can be used in such a way that instead of amplifying it will start oscillating. So, what are those criteria? These criteria were called Barkhausen criteria, right, that was we have seen in the last module. So, to quickly recall what is Barkhausen criteria? Barkhausen criteria is that we have open loop gain equal to 1 or gain equal to 1 and a feedback factor. So, gain into feedback should be equal to 1, right, that was the criteria. Gain into feedback should be equal to 1. So, mode of A into beta equal to 1, that is what we have seen. Second thing what we have seen is the phase shift. The phase shift, that is the voltage from the output which is fed through the feedback network back to the input, that should be in phase. The output voltage which is fed to the input of the oscillator should be in phase with the input signal, right. So, the phase should be 0 degree. Two things we have seen, correct. Then we have seen that if I have an amplifier which is an inverting amplifier, in that case if I apply a input signal, the output signal will be out of phase with respect to input signal, that is 180 degree out of phase. So, what can I do? I have to again change a phase. So, that 180 degree phase shift one more we have to add, that comes through the feedback network. So, output is 180 degree, feedback is 180 degree. So, total is 180 plus 180, that will be 360 degree or 0 degree. That means, your output part of the output voltage which we have fed back to the input is 0 degree, correct. So, we have seen that kind of oscillator, and that was our phase shift oscillator, right, and we have seen that in the phase shift oscillator we had 3 R and 3 C, because we have adjusted the value of R and C such that each R and C will give us 60 degree phase shift. So, if we use a inverting amplifier in phase shift oscillator, we had 180 degree output, this 3 R C will give us further 180 degree. So, when we feedback through this R C, we will get 0 degree or 360 degree, we have seen that, right, and we have also seen an example. Now, today let us see another kind of oscillator, and that is called Wein bridge oscillator. Wein bridge oscillator. In this oscillator, the output is in phase with the input. The output voltage, output signal is in phase with the input. That means that the feedback network should not give any kind of phase shift, right, because same phase is our output. We have to feedback, let us say this is a feedback network, we have output, right, this is a feedback network. Now, you have this amplifier, it goes, it comes back, it feeds the feedback network, comes back, right. So, this is what we have seen. If you come to the screen, I can explain you in a better way. So, what I am showing you here is that you have an amplifier, you have a feedback network, correct, and you have this signal, that is your Vs, this is your Vi, this is coming from the feedback network beta, this is your amplifier, and this is your output voltage. Part of the output voltage is feedback to the feedback network. We have seen that, right, we have seen this. So, what I am saying is, if your amplifier, right, the amplifier has no phase shift, the output is in phase with respect to input, then this beta should not give any further phase shift, because the signal, the part of the signal that we are providing back to the input, right, that is also 0 degree. So, the signal that is coming over here should also be 0 degree. So, this kind of amplifier where there is a phase at the output signal is in phase with respect to input, we will see this kind of oscillator in which the amplifier will not have any kind of phase shift. Okay. So, let us see that kind of oscillator, that is called Wein bridge oscillator. What is called? Wein bridge oscillator. Okay. This is a circuit, we have used electronic devices and circuits for taking the particular schematic. Now, Wein bridge oscillator is an audio frequency sine wave oscillator of high stability and simplicity. Okay. So, it is an audio frequency sine wave oscillator, audio frequency sine wave oscillator. It has a 2 RC stage, right, 2 stage RC amplifier circuit connected in a Wheatstone bridge, with an amplifier stage, right. So, you see there is one RC here, there is one RC over here, and there is a amplifier stage, correct. So, you have 2 RC circuit connected to the amplifier stage. Okay. Next one we have to remember is it uses a non-inverting amplifier. So, when it is non-inverting amplifier, the output will be in phase with respect to the input, correct. So, it uses a non-inverting amplifier, hence does not provide any phase shift, you see, right. So, no need of phase shift through the feedback network. Since it has no phase shift, the feedback network should not also provide any kind of phase shift. The circuit is shown here. The output of the amplifier is applied between terminals 1 and 3. So, you see terminal 1, terminal 3, right. This is the, you see where is connected, it is connected to the output of the amplifier, right, output of the amplifier, because this is grounded, right, 3 is grounded, you see amplifier is also grounded, right, output of amplifier, this is how we take the voltage. So, the output of the amplifier is connected to 1 between terminal 1 and 3, that is what it is written here. Second is the amplifier input is supplied from the diagonal terminals, you see the input of the amplifier, the input of the amplifier is supplied from where, from 4 and from 2, from 4 and 2, right. So, amplifier input is supplied from diagonal terminals 2 and 4 of the Wheatstone bridge, right. The resistor values are adjusted in a way that input amplifier must not be 0 or non-vanishing, right. The RC network is responsible for determining the frequency of the oscillator. So, RC network, that is 2 RC network, first one is here, second one is here. This RC network are responsible for determining the frequency of the oscillator, right. So, the 2 RC network arm, that is R1 C1 in series, this is the one, right, and second arm, that is R2 and C2 in parallel, you can see this one, are called frequency selective arms. What is called? Frequency sensitive arms, because that 2 arms are responsible for selecting the frequency of the oscillator. Okay. So, what we learn about the Wein bridge oscillator, that this Wein bridge oscillator is used as a audio frequency sine wave oscillator. Second thing is that the 2 RC amplifier circuit is connected in Wheatstone bridge connection. Third thing is the amplifier is a non-inverting amplifier. Fourth thing is the output is feedback, output is feed to between terminals 1 and 3. Fifth thing is the input of the amplifier is applied between 2 and 4, right. Then next one is resistor values are adjusted in a way that input to amplifier must not be 0 or non-inverting, must not be 0 or non-inverting. Okay. So, that are the few points that we have to remember, and finally, what we have to remember, that the R and C network is responsible for determining the frequency of the oscillator. So, if you understand this, then let us first look at the feedback network. So, what was the feedback network? One R and C in parallel, second R and C in series, right. So, one you see R1 C1, this is our Z1, R2 C2, this is our Z2, right, input voltage is fed between terminal 1 here and here, output voltage is between 4 and 2, you can see here this is your feedback voltage, correct, this is a feedback voltage to the amplifier. So, to understand the gain of the feedback network, let us consider this particular feedback network as shown in figure. This configuration is also called lead lag network. Okay? Lead lag network. So, you can be asked, do you know oscillators in which the feedback is lead lag? Then you can say yes, we have seen an oscillator which is called Wein bridge oscillator, in which the feedback is a lead lag network. Okay, because it acts like a lead at very low frequencies, while at a high frequency it has a lag network. It is very obvious, right, from the circuit, at low frequency it will have a lead, and at high frequency it will have a lag. Now, let us consider the gain of the network. So, what is the gain of the network? For understanding the gain of the network, we have to understand that this RC, series RC acts as Z1 and parallel RC acts as Z2. Okay. What we have to understand? Series RC would act as Z1 and parallel RC would act as Z2. Okay. So, where Z1 is, what will be Z1? If I write, Z1 will be R1 plus C, right, capacitor is 1 by j omega C1. So, if I solve this, what will I have? I will have 1 plus S C1 R1 divided by S C2, right, where S is nothing but j omega. Okay, S is nothing but j omega. Here we have considered S equal to j omega. Same way for Z2. Z2 is parallel, R2 is parallel to C2. So, Z2 is R2 parallel to C2. When you solve this, you can again reach to this equation, where Z2 is nothing but R2 divided by 1 plus SC2 R2, where S is nothing but j omega. Okay. So, it looks like this one, right, it looks like Z1 Z2 and then Vf and then Vin. So, the simplified circuit is shown, which is shown right over here. This is what? This is nothing but your voltage divider, right. If you have two resistors, you are dividing it, see, voltage divider or potential divider circuit. So, if I want to measure the voltage, right. So, beta is nothing but Vf by Vin is nothing but Z2 plus Z1, Z2 divided by Z2 plus Z1, right. How? So, because you see Vf equals to Z2 by Z1 plus Z2 into V in, right, into V in. So, what is my beta? Beta is nothing but Vf divided by V in, which is nothing but Z2 divided by Z1 plus Z2. This is what is written here, correct. This is what is written here. Now, let us substitute the values of Z1 and Z2, right. Let us substitute values of Z1 and Z2. What is Z1? Z1 is 1 plus SC1 R1 divided by SC1. Z2 is R2 divided by 1 plus SC2 R2, right. So, if I substitute these values of Z1 Z2 into beta, what will I have? Beta equal to VO by VI equals to, so I substitute these values and then I substitute j omega instead of S, right. This S is replaced by j omega wherever it is there, it is here, right. So, I am replacing it. So, what will I have? I will have this particular equation which is shown here, right, this one, correct. And then if I rationalize this equation, then we can get this particular equation, right. You solve it, you will get this equation. Now, what are the bifurcation criteria? The bifurcation criteria is to have 0 phase shift, right, 0 phase shift. What we have learned earlier also in phase shift oscillators, that when we want to have a 0 phase shift or we want to have 360 degree phase shift, the imaginary part must be 0. the imaginary part must be 0. We have learned this earlier, right. So, here where is imaginary part? Imaginary part is j 1, this one, right, here you see where there is j is the imaginary part. So, I will write omega 1 minus r square r 1 plus into r 2 C 1 C 2 equals to 0. So, omega square equals to r 1 r 2 C 1 C 2. Now, what is omega? Omega is nothing but 1 by 2 pi f, right. So, or f equals to 1 by 2 pi omega, correct, 1 by 2 pi omega. So, f would be nothing but f here would be 1 by 2 pi, right, under root of r 1 r 2 C 1 C 2. Why under root? Because omega square is there, right. So, under root of r 1 r 2 C 1 C 2. This is the formula, what we have to remember when this is the case of a Wein bridge oscillator. Okay, this is a frequency formula. Hence, the frequency of oscillator shows that the components R 1 R 2 C 1 C 2 of the frequency sensitive arms are the deciding factor for the frequency. What we understand from this equation? That changing the value of R 1 and R 2 and C 1 and C 2, we can change the frequency or we can decide the frequency. Okay. So, in case when your R 1 equals to R 2 and your capacitor C 1 equals to capacitor 2, my formula f would become 1 divided by 2 pi under root of r square c square. This is nothing but 1 divided by 2 pi r c, right, when my R 1 equal to R 2 and C 1 equals to C 2. Okay. So, that is formula that is given here, f equals to 1 by 2 pi R c. So, the gain of the feedback network becomes, so beta is V o by V I. So, I substitute the value, right, on substitute value of omega equal to 1 by R c, I will have beta equals to 3 by 9. I will have beta equals to 3 by 9. This is nothing but 1 by 3, right. So, what is the second criteria? Magnitude of A into beta should be equal to 1, right, or we can say greater than equal to 1, because initially we are keeping it greater than 1, then it adjusts itself to equal to 1. So, that the oscillations are sustained, correct. This is what we have learned. So, in this case, if that is a thing that we have to get and this is our beta, then obviously my gain, right, into beta is 1 by 3 should be greater than equal to 1. So, that means A can be 3, right, or greater than equal to 3 we can write. So, that means I will have A into beta. So, 3 into 1 by 3 is equal to 1, right. This is what is written here, right. Once I know what is beta, I should find A and that should be greater than or equal to 3. This is the required gain of the amplifier stage without any phase shift. Okay. This is the required gain of the amplifier stage without any phase shift. So, this is how we will solve for the Wein bridge oscillator. What we have seen, the beta equals to 1 by 3 in case of Wein bridge oscillator and my gain is 3, or if I write greater than equal to 3, then beta equals to 3 by 9, my gain would be greater than equal to 3. Okay. Now, that was the condition when my R 1 was equal to R 2 and C 1 was equal to C 2. What if my R 1 is not equal to R 2 and C 1 is not equal to C 2? In that case, how my equations would change? Okay. So, let us see that. R 1 is not equal to R 2 and C 1 is not equal to C 2, then my f equals to 1 by 2 pi under root of R 1 R 2 C 1 C 2. On substitution we get beta equals to V o by V I, right, and we have this equation. Now, from sustained oscillations A beta should be greater than 1. So, A would be nothing but 1 by beta greater than this particular value, right, or inverse of this, right. So, what is the advantage of this? Advantage of Wein bridge oscillator is that by varying two capacitors, if we vary two capacitors simultaneously, right, different frequency ranges can be provided. We can have different frequency range if we can change the value of the two capacitors. Advantage of the Wein bridge oscillator, easy, super easy, right. Now, let us see further. If the amplifier circuit using transistor is replaced. So, we are not talking about transistorized circuit here in this particular course, we are only talking about the operation amplifier based circuit. So, if the amplifier circuit using transistor is replaced by op amp with the basic feedback networks remains as the Wein bridge circuit, right, the basic feedback network, this is our feedback network which is our Wein bridge circuit, correct. This is the operation amplifier that we are using, right. So, of course, with this RF and RI, this is our feedback network, right. These are feedback network R1 C1 series, R2 C2 parallel is our feedback network, right. So, what is written here? If the amplifier circuit is replaced by op amp with basic feedback network remains as Wein bridge oscillator, one Wein bridge circuit, the oscillator is called Wein bridge oscillator. What is called? Wein bridge oscillator. Okay. The circuit is shown in figure below. The resistance R and C are components of the frequency sensitive arms. This R and C, R and C. Here we consider R1 equal to R2 and C1 equal to C2. That is why we have written just RC instead of R1, R2, C1, C2, because R1 equal to R2 equal to R, C1 equal to C2 equal to C. Okay. This is the circuit what I was talking about. Okay. Now, the resistance R and capacitor C are the component of frequency sensitive arms, resistance RF and R1 are the part of the feedback path, right, are the part of the feedback path. The gain of op amp. So, where is the input? Input is coming to the non-inverting amplifier. So, non-inverting amplifier gain we know, gain is nothing but A equal to 1 by RF by RI, right. We have seen that earlier. In the case of non-inverting amplifier, our gain is 1 plus RF by R1. Now, according to the oscillation conditions, what should be my gain? My gain should be, you remember, right, gain should be greater than or equal to 3 and my beta, that is feedback network, should be 1 by 3, right. Feedback network should be greater than or equal to 1 by 3, we can write like that, right, or in fact beta was 1 by 3 and gain equal to 3, right, we have just seen. So, according to oscillation conditions, gain should be greater than or equal to 3. Now, what is gain? Gain is 1 plus RF by R1. So, 1 plus RF by R1 is greater than or equal to 3 or RF by R1 is greater than or equal to 2, right. RF by R1 should be greater than or equal to 2. Now, what does that mean? Thus, the ratio of RF and R1 should be greater than or equal to 2. You see here, right. What does that mean? The feedback resistor RF, input resistor R1 ratio should be greater than or equal to 2. That means, my RF, if I select RF equal to 100, my R1 can be 50. Okay. Then RF by R1 will be nothing but 100 by 50 will be nothing but 2. So, it can be greater than or equal to 2. So, this condition would be satisfied, right. This can also be, RF can also be 150, then I will have RF by R1 equal to 3. So, it is greater than 2. So, still the condition is satisfied, you got it, but it should not be reverse, it should not be like RF equals to 50 and R1 equals to 150 and then I will have the value as 50 by 150, this is nothing but 1 by 3. This is not correct condition, okay. This is not correct condition because 1 by 3 is less than 2, right, 1 by 3 is less than 2, you got it. So, super easy, right. What we have to understand that RF by R1 should be greater than or equal to 2. Okay. Frequency is f equals to 1 by 2 pi RC, right. Why? Because actually frequency formula what we found is f equal to 2 pi under root of R1 R2 C1 C2. But what is the condition that we have selected here? R1 equal to R2 equal to R, C1 equal to C2 equal to C. So, f equals to 1 divided by 2 pi under root of R square C square. So, R square C square under root will become 1 divided by 2 pi R C. This is what we have seen here, correct. The feedback is given to the non inverting terminal of the op amp to ensure the phase shift is 0, right. The feedback is provided to the non inverting terminal of the op amp to ensure the feedback. You see feedback here is provided to the non inverting terminal, is provided to the non inverting terminal. Okay. So, if that is the case, if we learn how the Wein bridge oscillator operates, then let us solve some problems, right. Let us solve some problems. So, what is the problem 1? Example 1 is determine whether the circuit shown in figure below will work as an oscillator or not. If yes, determine the frequency of the oscillator, right, will work as an oscillator or not. If yes, determine the frequency of oscillator. Okay. Let us see. So, we have RF R1 non inverting amplifier, we have R and C in series, we have R and C in parallel. That means, this looks like Wein bridge oscillator, it looks like Wein bridge oscillator. So, if that is the case, first let us see what is the gain, right. We are given RF value is given, R1 value is given. So, let us substitute the value. Now, this is non inverting amplifier, non inverting amplifier we already know the gain is given by A equal to R1 plus RF by R1. So, let us substitute value 1 plus what is RF 6 kilo ohm, what is R1 2 kilo ohm, 1 plus 6 by 2 equal to 4. Okay. So, if the A equal to 4, what we found? A is equal to 4. Now, what is the condition? A should be greater than or equal to 3. So, this condition is satisfied, correct. This condition is satisfied. So, this satisfies the required oscillation criteria. The feedback is given to non inverting terminal ensuring the phase shift of is 0. See, feedback is given to the non inverting terminal ensuring phase shift is 0. Hence, the circuit will work as an oscillator. F equals to 1 by 2 pi RC. So, let us substitute value of 2 pi and RC. 2 pi R, what is R? 5.1. Why? Because here R is same. What is C? 0.01 microfarad. Here C is same. So, F will be 31.2068 kilohertz. This will be the frequency of oscillation. Okay. Now, what we have seen until now, let us complete this module here and we will see in the next module the another kind of oscillator. So, what we have seen until now we have seen that how you can design a Wein bridge oscillator using operational amplifier, right. What we have seen how we can design a Wein bridge oscillator using operational amplifier, and then we have seen that in case of Wein bridge oscillators the feedback is the output is in phase with the input, therefore, the feedback should not provide any phase shift, the feedback should not provide any phase shift. Okay. Then we have seen then in the case of Wein bridge oscillator the gain into beta, right, that condition should be greater than or equal to 1. So, gain would be greater than or equal to 3, beta would be equal to 1 by 3, right. Then we have seen an example how we can solve or how we can determine whether a given circuit will work as an oscillator or not, that too particularly Wein bridge oscillator or not, right. Same way we can determine if it is a phase shift oscillator whether the given circuit will work as a phase shift oscillator or not. Okay. So, this is how you can determine or you can understand the functionality or the working of the Wein bridge oscillator, So, in the next module let us see how the another kind of oscillator works, that is their LC oscillator. What is that? L and C. Here what we have seen until here R and C, whether it was phase shift oscillator? RC, 3 RCs, right. If it is Wein bridge, 1 RC in series, 1 RC in parallel. Now, we will see LC oscillators. Okay. So, just go through this particular module, understand it thoroughly, right, and I will see you in the next module with a new kind of oscillators or new class of oscillators to learn. So, let us learn in the next module what are the LC oscillators. Till then, you take care. Bye.